Welcome to this explainer. If you build microservices, or maybe you're prepping for a senior engineering interview, you're going to want to grab a notepad for this one. Today, we're putting on our distributed systems architect hats and doing a full system autopsy on one of the most frustrating and honestly fascinating production outages you'll ever face. We're looking at a phenomenon that literally turns your own safety mechanisms against you.
Picture this visceral, real-world scenario pulled straight from our sources. A downstream dependency degrades for 90 seconds. Your monitoring catches it, the on-call rotation gets pinged, and then the dependency recovers. Your dashboards turn a beautiful, healthy green. But your platform? It stays completely down for another 40 minutes. It feels like a brand new incident, but it's not. It's actually a massive, self-inflicted denial of service attack driven by your own architecture.
So the dependency recovered, right? The dashboards are green. Why did the system just completely collapse at the exact moment of recovery? Well, that's the core mystery we're solving today. Because by this point, the original fault is actually irrelevant. The system didn't fail because of the initial database blip. It failed because of how your system reacted to that blip. Specifically, your recovery logic, your retries, became the outage.
Section 1, Anatomy of an Outage, the retry.
To really diagnose this pathology, we need to understand the basic mechanism of a retry. Now, retries are absolutely not a bug. They're a deliberate, highly necessary resilience pattern. Networks drop packets, background daemons cause multi-millisecond hiccups, services have brief transient failures. A retry handles all that noise gracefully without failing a user's request. It's kind of the system equivalent of an angry user mashing the F5 refresh button when a web page stalls, right? You try, it fails, you try again a moment later, and bam, it succeeds. Sounds simple enough, but at scale, that simplicity hides some catastrophic danger.
Which brings us to Section 2, the retry multiplier effect.
The fundamental issue here is that retry logic is almost never designed as a unified system. Instead, it's written by individual teams completely scattered across multiple, uncoordinated layers of your tech stack. Each layer acts as a silent multiplier. You've got built-in retries hidden away in your client SDK. You have Envoy or Istio service mesh proxy policies. You've got developers writing manual try/catch loops in the application code itself. And down at the very bottom, your database ORM and connection pools are doing their own reconnects. Every single one of these layers is just trying to help by retrying, but they have no idea the other layers are doing the exact same thing.
And this is where the math gets truly terrifying. A single user clicks a button, the application code retries a failed query, but what you don't see is that the ORM is retrying inside the driver, the connection pool is attempting to reconnect, and the pool itself is retrying that reconnect. Suddenly, you're firing 4 or more retries into a degraded database from just one transaction. Now multiply that by every active connection in every pod across every single region. You are literally generating tens of thousands of requests out of thin air.
Moving on to Section 3, hitting the recovery cliff. Let's look at the exact moment your system flips from degraded to totally destroyed. Step by step, here's how the storm forms. First, a service drops. Second, thousands of clients fail at the exact same wall clock moment and silently start their retry timers in parallel. While the service is down, load balancers are just rejecting these requests, so the service itself feels no pressure. But step 3, the service recovers. The health checks finally pass. And step 4, the millisecond that load balancer reopens the pool, that entire synchronized backlog of thousands of queued retries hits the recovering service all at exactly the same time. The crazy thing is, this is practically invisible to traditional steady-state monitoring. The service is instantly crushed again. Why? Because you provisioned your infrastructure and tuned your autoscaling for normal, steady-state peak queries per second. You definitely didn't size your thread pools or database connections to handle a massive, simultaneous reconnect from your entire client population in a single millisecond tick. Autoscaling takes minutes to spin up new pods. A retry storm will destroy your service in 1 second.
All right, Section 4, why exponential backoff fails.
Now you might be sitting there thinking, hey, I know how to fix this. I'll just use exponential backoff. But the math here is simple enough to be really deceptive, and our sources heavily warn against relying on this alone. Pure exponential backoff actually just synchronizes predictable wavefronts. Think about it. If 1,000 clients fail at T0, they all retry at 1 second. Then they all fail again and retry at 2 seconds. Then 4 seconds. You haven't dispersed the traffic at all. You've just organized it into coordinated, deadly waves that will take your recovery down again and again. The true fix, the architectural absolute must, is back off with decorrelated jitter. Jitter adds randomness to the interval. It smooths out that giant synchronized spike into a manageable distributed curve of traffic.
Section 5. Real-world configurations. Let's ground this theory in some production reality. We can look at where these storms actually form in popular stacks. This isn't just theoretical. It's hiding in the YAML and SDKs you're probably using right now. Whether it's the hidden default retry mode configurations in the AWS SDK, transport layer retries baked right into Google Cloud libraries, or STO service mesh configs that someone set during onboarding and literally never looked at again. These are the real-world triggers. The Google SRE book even strictly advises implementing a 10% client-side retry ratio limit to throttle this exact behavior. You have to audit these vendor defaults because they are out there retrying on your behalf, completely out of sight.
Section 6. Architectural retry discipline. To actually prevent these outages, we have to completely dismantle the myth of smart retry logic. Writing a clever try/catch block in one microservice is not going to save the system. We need to prescribe architectural discipline across the entire stack. First up, we use circuit breakers. The crucial point here is that when failures are sustained, the circuit breaker opens and instantly rejects traffic. It fails fast. This holds clients off and stops the useless retries, which gives your degraded service the actual breathing room it desperately needs to recover, rather than spending all its limited CPU cycles just rejecting connections. Second, we enforce token bucket retried budgets. This is absolutely vital. You apply a strict quota per client and per service. When a service exhausts its retry budget, let's say it's already retried 100 times in the last minute, the system just stops retrying voluntarily. It bounds the worst-case scenario at design time, cleanly cutting off that amplification loop right at the source.
Section 7. The production checklist. So, as a staff engineer, what is your concrete blueprint for preventing this self-inflicted DDoS? Here is your actionable production checklist. Number 1. Decorrelated jitter must be the default everywhere. Number 2. Strict token bucket retry quotas. Number 3. Circuit breakers to fail fast. Number 4. Aggressive load shedding during the recovery phase. A lot of teams actually stop load shedding the second the health check turns green, which is exactly when you need it most. And number 5, ensure your clients actually obey a retry after each TTP headers to properly coordinate the reconnect.
When you're debugging or auditing your systems, you've got to walk the entire stack sequentially. Start from the client SDK, move to the proxy mesh, then check your application code decorators, and finally dig down into the ORM and background job queues. The storm always forms wherever these layers compound with coordination. You must map exactly where every single retry lives.
Section 8. Key lessons learned. Let's summarize the really crucial takeaways from our system autopsy today. The fundamental lesson is that retry policy cannot just be a tactical try/catch block written by an individual developer trying to make their specific service robust. If it's isolated, it's dangerous. Retry policy must be a first-class architectural concern. It needs to be enforced through platform standards, mesh defaults, and really rigorous code reviews. As the architect from our sources powerfully points out, discipline beats intelligence every single time. The smartest, most complex retry logic is not what recovers your system. The strictest, most bounded discipline does. So I want to leave you with this final, provocative thought to investigate with your teams this week. Before your next major incident, can you confidently map out every hidden retry layer currently active in your production stack? Because if you can't, well, your recovery path is very likely your next outage. Thanks for joining me on this explainer, and seriously, go start auditing those vendor defaults today.